also make it. It's also a checklist for you about to check what you know, what you don't know, or maybe I should check up and learn something again. Okay, so what we started out was mostly we did scalar fields. So we started out with one scalar field and then we graduated to systems with many scalar fields, and we saw how to write Lagrangian densities for these guys. And then we learned to, given a Lagrangian density, to work out the Euler-Lagrange equation of motion. And then we also did a bit of playing around with solutions. So we looked at classical vacua, these were, we defined these to be the lowest energy configurations, and we also looked at other solutions like we look for things like time independent, finite energy solutions, and we saw that this was only possible in one dimension, one spatial, in 1 + 1 dimensions, and it was not possible in any higher dimension. Okay, and we saw a nice example of it. We saw the kink soliton or the kink solution in 5-4 theory. Okay, we saw that, and so this was called Derrick's theorem or whatever, right. Then we also studied symmetries, and we saw how groups group theory was essential in describing them or useful. And then we did symmetries. We also saw that continuous symmetries implied conserved currents, and this was called Noether's theorem. Okay, and then we discussed symmetry breaking. Or what we call hidden symmetry, and this was nice thing we saw was there was Goldstone's theorem, and so here another mathematical concept which we had seen in an abstract setting came into use. We saw that when you have continuous symmetries which are broken down, then you there is a use for the coset spaces. So Goldstone's theorem is best stated in the language of coset spaces, cosets or coset spaces. And we also saw a brief discussion on what happens in quantum field theory. We didn't prove anything, but we sort of saw that there were issues with and discrete and continuous symmetry breakings work different. There was the dimension dependent statement, and that was the Mermin-Wagner-Coleman theorem. And of course, the way we derived Noether's theorem, it was valid for not just scalar fields. We didn't make any assumption on about the field, and so clearly it holds for much more general situations. But the way we went beyond scalar fields was scalar fields So all these symmetries which we looked at, we call them we redefine them to be global symmetries because they did not depend on space and time. So, the route we followed is to look at local symmetries okay. We only looked at internal symmetries, and this implied the need for a gauge field or a vector field for vector fields. Okay. One may think, do I need to go through this method? Can I ad hoc say I can my basic field is a vector field? Nothing, actually there is nothing wrong with that. It turns out that so suppose I started out with a vector field for electromagnetism, say, and it's perfectly a good field, except that if you try to write a Lagrangian for this guy, what you would end up getting is, so you would say I am allowed two derivatives. So, taking this already has one index, so I could write things like, so this would be an object which has a derivative of this thing. So, we have to construct scalars out of these guys, and I could since this is just a second rank tensor, I can break it up into symmetric and antisymmetric parts, and the antisymmetric part I will call it f mu nu, and the symmetric part let us just call it S mu nu. So, if I try to write out a Lagrangian, the most general Lagrangian which would involve two derivatives of these things would have some coefficient here, let us call it C1 f mu nu square plus C2 S mu nu S upper mu nu, and you cannot have a cross term because that vanishes. One is symmetric, one is antisymmetric. If you try to contract them, you get 0. So, you get two different kinetic energy pieces plus anything, plus arbitrary function of a mu's, as long as it is some Lorentz scalar. For instance, I could write something like a mu whole square perfectly. So, this is what you would have done if you just tried to use the ideas that you had for a scalar field. You are just saying you have a vector field and you know that you want your Lagrangian density to be a scalar, and you just go ahead, put in the restrictions on derivatives, etc., exactly like we did, and then you see already that at the level of kinetic energy there are two different possibilities. Okay. And so, in fact, you could go ahead and say, can I construct quantum field theories out of this? And people actually spent a lot of effort trying to quantize these theories with this kind of terms, and these theories turn out to be sick quantum mechanically. So, in quantum mechanics, what is sacrosanct? You want to have a Hilbert space in which everything is positive definite. You do not want states with negative norm, and they are called ghosts or whatever. So, these theories had a lot of problems with those kind of issues. And so, if you just write ad hoc, write a theory like this, as far as we know today, that these do not make sense quantum mechanically. Okay. So, but as if you want to write a classical field theory, you can go ahead and do this, but what you get out of local symmetries is something very different. It says that there is an extra thing which is gauge invariance, or local, we will call gauge invariance, or we will call it local invariance. Okay. So, the extra ingredient that you need when you come to vector fields is that we will call it the gauge principle, okay. And this we know from electromagnetism, the fundamental objects were electric and magnetic fields, and it was not a mu. So, we saw that if you get two different, so in electromagnetism, you know that if you give a mu of x and another a mu prime of x, which is a mu of x plus some d mu of some scalar of, okay, both of them give the same electric and magnetic fields, and we know that they are we would say that these two are gauge equivalent, they are the same. So you have to impose the so in other words, so this, so you require, so and we also got the same transformation by converting global symmetries to local symmetries. When I did the SO2 it looked exactly like electromagnetism, but we will see that in more general cases it means something, it gives something much more general called Yang-Mills, but right now we are not getting into that. So the idea is that we have to put in the gauge principle. What does the gauge principle do? First thing it does, it tells you C2 has to be 0. It implies that C2 should be 0. Okay, and it also says that there is a function like this is again obviously not gauge invariant, it is not invariant under local symmetry transformations or gauge invariance. I will keep using these two interchangeably. Okay, and it also says that f should be 0. So if you restrict yourself to two derivatives, this is it. You do not have any more freedom. This is the only term you could have written with the derivative restriction. If you have higher derivatives, of course you could write more terms, but like I discussed in the beginning of this thing, even for scalars we never looked at higher derivative things. Okay, this is a restriction we are putting it in, and there are situations where you go beyond two derivatives, but we will not in this course. Okay, so you can see that so we need one extra ingredient to generalize this whole structure to include vector fields, and vector fields come naturally in this sort of, when you try to do a local this, it comes through a gauge invariant part. So it is not just this, so this is just the kinetic energy for the gauge field, okay, but there are interactions, in other words there are cubic terms. So anything, any term which is not quadratic in the fields, we will think of them as interactions. From the viewpoint of quantum field theory, you always expand about things about a quadratic and the rest you treat as interaction. So it is a very perturbative quantum field theoretic viewpoint. So we will say that if there is a cubic term or a quartic term, we will think of them as interactions. So if you have a scalar field with a term like m square phi square, that is not an interaction, that is a mass term, but if there is a phi fourth term, that is an interaction because it involves 4 fields. You also know that the equation of motion becomes nonlinear then. Okay. So similar, so now if you go back and look at what we had done for the SO2 example, you naturally see things. So when you look at terms like this, d mu phi star or phi bar, what did I call it? Phi star or phi bar? Phi bar. Okay, I called it phi bar. Okay. If you expand this out, you will see there are terms. So if you, let us write this out, it was d mu we did expand this last time. Okay, but what I want to point out is, say, take a term like this, q a mu d mu phi bar. So you have a term which looks like this. Okay, so you can see that this particular term is cubic in the fields. It has 2 scalar fields and 1 this thing. So interactions. So the gauge principle does 2 things. Huh? Are we okay now? Thanks. Fine. So you can see that even so you, one part is Ke is this, you can see this gauge principle tells you this, but it also does not sort of let you freelance and write random things. It gives, so interactions also built in. Okay. So in some sense, if you are a minimalist, in the sense that you do not want to do anything more than beyond this sort of this thing, this is where you take this kind of approach very seriously. unless you have some other way of constructing situations where you get some other interactions which are gauge invariant, but they are very much more complicated. Okay. And so that there are situations where this happens, but this straight ahead approach actually works well, and it works so well that it leads you to a framework where you can describe all the basic interactions in basic fields, rather the interactions, forces in nature. We can describe all of them except bar one. Guess which one? Gravity. Okay, gravity, there is an issue, but forgetting gravity for the moment, in fact it is so successful that there is something called a standard model. Okay, a standard model which is based on extending this to more complicated settings. And by the way, in this whole course there will be no fermionic fields. That is because I do not want to add a plethora of indices as if there is not enough. Okay. So the idea is to simplify it, and this is an undergraduate course. So I do not want, I mean this is an essential simplification, but in some sense all the concepts can be illustrated without that. Okay. So for instance, you would have seen in your assignment that you can discuss spin of a photon or helicity of a photon. You can discuss without, I mean fermions are not the only things which carry spin. Okay. So the key point is interactions with are built in. Okay. And so the thing about the standard model is that more or less bulk of it was done more than 20 years ago, and I mean right now people are only building more and more things to check tests, what are called precision tests of the standard model, to look beyond the standard model, to know what is coming beyond that. But so far as we can tell, all experiments in high energy physics, this approach has been more than enough. That, I mean, it is shocking or amazing or whatever, I do not know what word to use, but this is the status, and that is why we will in this course we will take this viewpoint, and now we will push it further to examples where the gauge group is not just an abelian SO2 or U1, but could be any group. Okay. So what we will do to understand, so the next part of this course will include settings where we have vector fields as well as scalar fields in your theory, and we will input will convert global symmetries to gauge or to local symmetries and see what happens, and we will go through this whole thing. For instance, we saw already for the abelian case that if you are in a setting where symmetry breaking happens, what happens in the presence of a gauge field is rather different from what you saw when it was a global symmetry. So it leads you to the Higgs mechanism. So we will see interesting things, and we will also see how that we could go around Deriv's theorem. Okay. One easy way to understand it is Deriv's theorem assumes that the only fields in the thing was scalars, and there is no gauge principle out there or anything. Okay. And the thing is, again there will be a nice feature which will come whenever we are looking at finite energy solutions, time independent. I do not call them, I mean I am not allowed to call them solitons, because solitons are supposed to have some non dissipative nature, but I will on and off keep calling them solitons. And I would recommend you read Sidney Coleman's Eriche lectures. He gives a very nice description of what should be a soliton, but I will be much more relaxed about my use of the word soliton. When I say soliton, you should have in mind time independent finite energy, at least these two. Okay, these two conditions we will use them interchangeably. So we will see that in every dimension a soliton has a different there's it's like there's a new twist in every dimension, and it sort of you get more space to do something new. And so we go from 0, 1, 2, 3 and even 4, okay, where we will sort of take time and make it Euclidean. So the space will be like R4, you get something called instantons. Okay. So that will be sort of the final part of this course. Okay. So before we do that, we need a little bit more structure, and that structure was already evident when we tried to understand try to write a good guess for how to parameterize the fluctuations when you have spontaneous symmetry breaking, and the structure that underlies that goes by the name of Lie algebras, and we have seen it in various forms. I have given you hints throughout these lectures. Now we will put all of them together and we will see that there is a structure called a Lie algebra. It is just a collection of whatever ideas you already know. Okay. So, I will just put them together and then you sort of write something more abstract from that, and we go on from there. Sort of, maybe I should call it an invitation to Lie algebras, because I am not really going to. So, the starting point is the following thing, which we already know some things. So, we saw that any SON group element can be written, let us say you have a group element of SON, we saw that that could be written as G power A, where A was an n by n antisymmetric matrix. Okay. And so, the point here is that what it tells you is that instead of looking at the group element, I could work equally well with antisymmetric matrices. Okay. Isn't that what this tells you? If you give me an SON matrix, okay, I can enjoy, I mean if you give me a group element by doing the inverse. So, that is the, so let us put it this way. So, there is this and there is the exponential map which gives you the group element, and there are some features of A which are not there in G. So, if I gave you two elements and asked you what is their composition rule, it is pretty complicated. Not that it gets easier out here, but at least we can write formally something, okay, and in some cases we can actually write the answer fast. Okay. So, this so the exponential map is a very important ingredient in this whole connection. So, what we will see is that the first point is that let us look at this. If you give me two antisymmetric matrices, at least for the next two half boards, when I use the symbol A, it just means antisymmetric matrix. Okay. So, one property is, you can see that if I take alpha A1 plus beta A2, that is also an antisymmetric matrix. So, this is roughly the structure of a what, a vector space. Okay. So, so let us write this out. So, the space of antisymmetric matrices n by n antisymmetric matrices with real entries for now is a real LVS. LVS is short form for linear vector space of what dimension? Okay. So, what we will see is that a Lie algebra is this kind of a linear vector space with some extra structure, and the extra structure is there is basically what comes from the axioms of a group. Okay. The first point is that if you give me two elements G1 and G2, okay. So, yeah, so before we even look at that, the key point is, suppose you look at the product A1 times A2, if A1 and A2 are antisymmetric, is the product antisymmetric? No, it is easy to see it is not, because if you take the transpose, it is A2 transpose A1 transpose, and these are minus of each other. So, it is equal to A2 dot A1. Okay. It is not antisymmetric, there is no structure, but if you take the commutator, okay, it is indeed So, let us look at the commutator, and what are the properties? It is linear in each of its arguments and it is antisymmetric. Okay. So, it is an antisymmetric bilinear operation. Okay. So we have a linear vector space, there is one more extra structure which is something which eats up two things, it is linear in each one of its arguments, and it is antisymmetric if you exchange this thing. Okay. This we will this has a formal name, it is a Lie bracket. So the abstract statement is there is a linear vector space which is equipped with a Lie bracket structure. There is a little bit more structure which I have to explain to you. Okay. So let us call this the Lie bracket, but in this course and in most physics applications, Lie bracket can be, you can blissfully think of the Lie bracket as being replaced by the appropriate commutator, because that is what will happen. Okay. Now the third part actually comes through the fact that we know that there is a group. So if you give G1 and G2 are two elements, and suppose G3 is equal to G1 dot G2, then G3 is also an element of the group, so it should be writable as e power some A3. Okay. But the product of two exponential matrices, as we saw earlier, have you seen it before in this course? Okay. So there is something called the Baker-Campbell-Hausdorff formula, and for once let me write out to the next order piece. Okay. Again the way I think of this thing is to put two lambdas here, it is like a formal bookkeeping device, and say that write out bunch of terms, and so I will say first order in lambda, second order in lambda, that will give you a nice way of tracking things and keeping track of when you are multiplying things to check things, right. You know that if you keep these two to correct some order, you can only verify this to that order. Okay. So what you should do here is to work out, you can show, so I will not prove it, I will just write something, put a lambda here, put a lambda here, go ahead and expand it, and then start collecting terms and re-exponentiating it. Okay. And that will give you A3, you know it has to combine back into that thing. So so the exercise, which is a rather tedious one, is to show that A3, of course this is the easy part, and the next part you would have seen in quantum mechanics usually quite often, is half A1 times A2, but I am going to write out the next order piece, and for once I need a piece of paper, I do not want to make mistakes. It is an infinite series, it does not terminate. Okay. So but this is something very, it is a concrete statement, it says if you give me two elements A1 and A2, I will give you a unique element A3, it is an infinite thing. Okay. And let us just define this to be some operation which we will write as A1 star A2. Okay. The reason to write it like this is because just as we defined the Lie bracket, so it is made up of objects and Lie brackets of those things. So in the abstract setting there is something which we will call a star operation, which gives you which is giving you the composition rule. Okay. But and I would recommend that you work out this piece. Okay. It is a good practice to play around with it, and if you there are I mean there is not a very clean way of writing this whole thing, there are some generating function methods, etc. But as far as I can see that I mean I have not personally found a use for things beyond this level. Up to this, yes, I have used it, and maybe I will leave you an assignment to do. So you can see now what so we have a linear vector space equipped with a Lie bracket and this kind of operation which tells you the composition rule. But there is still something more in the story. So if you go back to the group definition, there should be an identity. So what is the identity element here? The 0 vector. in the vector space, right. If you take the 0, okay, so that is the identity element. So, that is there. Okay. Inverse is easy, inverse is not a problem, but is there any other property that we have to associativity. So, that is the last property. So, we know so far. Okay. So, what about what does associativity imply? Okay. So, it implies some extra structure on this this Lie algebra, whatever we are defining. We will, I mean, after we put all these structures in, only then we have defined what we mean by a Lie algebra. Okay. So, now comes the so the thing is associativity. What does it tell you? You have G1 dot G2, you do it first like this, this should be equal to this at the level of group, and you are given this star operation. So, that tells you how to compose them. So, this so we already have achieved that. So, we have to put all these things together and ask what does this imply. Okay. So, this implies the following. So, let us write again, it is exactly like this. Let us say that G1 is e power a1, G2 is equal to e power a2, and G3 is e power a3. Okay. G3 here is not like this composition rule, it is just some 3 different elements. Okay. And if you go ahead and work this out, and you can check that what this implies is something as follows. So, for matrices, you know, this is true. If you give me any 3 matrices, they satisfy the Jacobi identity. So, this is just the okay. So, it is so now we have a definition of what we mean by a Lie algebra. It has all these structure. Okay. So, it has a linear vector, it is a linear vector space, but it need not be real, by the way, it could be complex also. Then so if it is a real vector space, we say it is a real Lie algebra. If we say it is a complex vector space, we say it is a complex Lie algebra. Okay. And and dimension of the linear vector space is defined to be the dimension of the Lie algebra. So, it is a Lie algebra, it is a linear vector space over some field equipped with a Lie bracket with this kind of with a composition rule which satisfies the Jacobi identity. So, this is the definition of a Lie algebra. So, what I have done here is to take our definition of SON and see all the properties of the fact that it was a group, and you sort of find that you get this structure. Okay. So, one more important point is that all these groups, for instance, we in one of your assignments you I think something like this. So, I gave you arbitrary 2 by 2 matrix with 4 numbers alpha 0, alpha 1, alpha 2, alpha 3 sigmas for the Pauli matrices, and I asked you the conditions under which u dagger was equal to 1 and determinant of u was equal to 1. So, this defined the group which we already seen, it is the group SU2, and if you worked out in your assignment, you will see that first thing it implies is that alpha 0 and alpha a have to be real, and further alpha 0 square plus alpha 1 square plus alpha 2 square plus alpha 3 square should be equal to 1. So, what it says is that the set of unitary SU2 matrices, SU2 is group elements, is in 1-to-1 correspondence with the points on a 3 sphere, because this is exactly 4 numbers subject to one relation. Okay. So, this is an equation for a 3 sphere. Okay. If this were not there, this would be a normal sphere. Okay. So, what you see is that all these groups, these are called Lie groups, because the space, the parameter space is actually a nice manifold. Okay. So, in this case it is a 3 sphere, and locally, and what this the Lie algebra tells you is sort of gives you locally what the directions are. If you know what it is, like the tangent space to this space. So, you pick a point here, it tells you all the different directions. You make it look like, so it is a S3 is a 3 dimensional manifold. So, you locally it looks like 3 space at every point you put some, it is a curved space, but okay, let us not get into that. But the point is there are 3 directions, and what are those 3 directions? Those are exactly, if you look, if you come back to SU2, it is actually similar to SO3. So, in fact this discussion will tell you that you have to look at, there is a subtle difference when you come to the group, but at the level of, so level of Lie algebra they are the same. SO3 also has the same structure, it is just here we would look at 3 by 3 antisymmetric matrices, and it is 3 dimensional, and this is also 3 dimensional. Okay. So, this will give you a Lie algebra. Okay. So, as groups SU2 and SO3 are not the same, but as a Lie algebra you would see that there is an isomorphism. Okay. In other words, locally it looks like. So, you can ask what is the precise, can you tell me the difference between SO3 and SU2? The answer is very simple, it is SU2 with an identification, at least this group manifold it has an identification to identify antipodal points. So, it gives you some space, do you know what it is called? RP3 or something like that. Okay. So, it is S3 with antipodal points identified. Okay. You can't picture it, if you want you can write it as an equation. Okay. You identify the opposite points. Okay. And so in other words, SO3 group element, every group element there will have 2 things. One, if you pick a point locally they are the same, but it is just that this point and its antipodal point which is on the other side will not be will be the same as a group element. Okay. We will see all these things in your assignment, and there are some notes, but so what I want you to remember is that the Lie algebras are much simpler because there is a vector space structure in that. So, you can add, subtract, you can do lots of things, nice stuff, whatever you could do with vectors. So, it makes life easy. Okay. And so, we have in this course through your assignments and through my discussions you have seen actually 3 families of groups, Lie groups. So, 3 examples which you have seen. By examples I do not mean one example is actually each one is a family. So, you have SON that you have seen, also SUN, these are n by n unitary matrices, but you also seen the symplectic matrices. Okay. And now so now books that you should be careful, some books have will write SPN and some others will write SP2N. Okay. And the only way to solve the ambiguity is to ask what SP1 stands for. If there is SP1 that is same as SU2 which you can prove, or you look at so you just look at the first case and you distinguish what their notation is. So, this is I mean there is no fixed notation on this, but the key point is you have seen all these things. Okay. So, they are all examples of Lie groups, and the interesting thing is this is not all, there are few more which are not in this list, and the classification is better when you go to the complex. Okay. So, complex Lie algebras, reals are more complicated. Okay. So, you find that you get these 3, but plus there are exceptionals. They are called exceptional because they are not part of any family, they occur only for some special cases. Okay. And Catan classification has some numbers, there is A, B, C, D. So, these you here you separate out SO2 the even case and the odd cases. So, they form A, B, C and D. Okay. I will not tell you which one is which, you go back and check. So, that covers these things, but you have E, F and G. Okay. So, G, then F 4 and G 2. Okay, there are some finiteness conditions. So, that is you will find that you will end up with only these kind of, these are the only examples of finiteness, simpleness. There are some conditions you need to put in, but basically this is it. And the amazing thing is, in other words, you know just about 99.9999999% of the Lie groups you already know. You have seen it in some form or the other, and these you will never see in this course. So, we will go back to only this. So, now coming back to Lie algebras in general. So, now we know that it is a linear vector space, and we can use some of the tricks we learnt in when we were working with linear vector spaces. What did we do? We said we will choose a basis. Okay. So, first thing is, before we do that, I will discuss what I mean by a representation of a Lie algebra. Okay. So, a Lie algebra is, I told you there is this whole structure which is there, and so the idea is that, so let us say that A belongs to, so let me use script L. A belongs to script L means that it is an element of a Lie algebra L, and it has all the standard properties. So, so the thing is that we could have, suppose A1, A2, so AI, let us say, for all. Okay. Suppose we have the Lie bracket of this thing. So, now if you find that if, so a representation for groups, we saw that if you give there is an abstract group multiplication law, we realized it by acting on it by some matrix. Okay. Similar thing is to find, so a representation of Lie algebra is, in the simplest way, is a matrix realization of the Lie algebra. Okay. So, in other words, if you give me the abstract element, I will give you some matrix, okay, and let us say this is some R by R matrix, okay, such that, okay, so and Lie bracket gets mapped to what? What should Lie bracket get mapped to? The commutator. So, it is like chicken and egg, right? We started out with a actually we started out with an n dimensional representation of the Lie algebra of SON, and then we worked out our abstract definition of the Lie algebra. Now, we are going back to this. The reason is that that is not the only realization of SON. Every time we wrote a tensor of SON, we are actually getting a different realization. It is a different representation of the same thing. Okay. So, Lie bracket becomes the commutator, and of course, it has to respect the Lie algebra structure. I mean, that is implicit in this statement. So, this is what you mean by a representation, and you would say this is a representation of dimension R, okay, where R is the size of the matrix, and it should be a faithful representation. For instance, there is one representation which will work trivially. Suppose I say that every AI gets mapped to matrix of zeros, it will satisfy all your conditions very trivially, but that is okay. So, you would like to get rid of those things, okay, and there will also be a notion of irreducible, in the sense that you cannot break it down to something smaller, okay. And you will see that again. So, now the thing is the group element, so the corresponding group element Gi will be realized as just e power m of ai, rather in this representation. So, that will, so we will write something like this, yeah. So, G we would have written as e power a, and this will go to m of G, that means the matrix realization of G will be equal to e power m a, okay. And in physics we never ever do the abstract stuff, we really always work with some representation, okay. And so we'll stay with that, I mean, okay. So now we can come back to the linear vector space setting. So I just want you to remember what a representation is. Now we will go back to a Lie algebra. So if you give me a bunch of AIs, since it is a linear vector space, I can choose a basis, okay. And so we can write any A. So choose a basis, okay. We can write this as AA TA, where TA span the linear vector space and A goes from 1 to the dimension of L. Okay. If you take SU2, you will have 3 such generators, or SO3 you will have 3 generators, okay. So this is what you get. So now we can ask what so the thing is, now because of the linearity of the Lie bracket, the structure, all the data which we have in the Lie bracket is captured by just by looking at what it does to the basis vectors. That is a big simplification, right. Always we saw that when any structure we put on a linear vector space, life became easy because we could only work with basis vectors and we could, okay. So what you do is, I could ask what is the Lie bracket of TA and TB. This has to be an element of the Lie algebra. So it should, which again can be rewritten in terms of these guys. So I can write it as some summation over C F A B C T C, again repeated index is summed over, again I respect upper, lower, etc. I do this, okay. And now there is an essential distinction between physics literature and math literature. In the math literature you do not put anything out here, in the physics literature we put an I, okay. So and these FABCs, they have all the data of the Lie algebra, because it tells you, okay. Of course it is basis dependent, but the key point is that this knows everything about the Lie bracket structure, okay. And you know that it has to be, so what do we know? We know that FABC has to be equal to F minus of FBAC, because that is the antisymmetric property of the Lie, okay. I leave it as an exercise, or it will show up in one of your assignments to show what the fact that this satisfies. So the T's themselves have to satisfy a Jacobi identity. So you take TA, TB, TC and write out the Jacobi identity, and you see that it will imply a condition for the F's, okay. So these have a name, they are called the structure constants, okay. So we'll give you, I'll give you an example now, and it will be in terms of a representation, and so then I will write TAs as matrices, and so TA now, so so the thing is, what I will do is I will use the same symbol T. I won't say, I won't do this M of AI, but I will write a matrix for you, okay. So let us take the case of SO3, okay, and I will write out for you A as a matrix, and I will give you a 3 dimensional representation. So SO3 A will go from 1 2 3, so there are 3 of them. I have to give you 3 such antisymmetric matrices. I will give you a very simple basis, which is, so B and C here are the labels of the matrix, okay. Okay. So T1 will be the matrix. So let us look at what T1 is. T1 will have zeros in the 1, okay. It is an antisymmetric matrix, so it has only these elements. So you can see for yourself, and you can so exercise for you is to reproduce, check what the structure constants are, okay. And again I must warn you, the way I have given you, you will get without the I, okay. If you want to get an I back, if you want to put an I back in here, I think you put a minus I here. So, this is like the physics literature versus math literature. Whenever you do a representation, we will look at we will choose the matrices to be Hermitian in physics, while in maths literature that is skew symmetric or anti-symmetric kind of. Okay. So, that is what is this. You can see, I mean, that this is convention dependent, of course, whatever it is, but this is a fun thing to just go ahead, take this particular example where you know these things, and you do not have to sit and do matrix multiplication. It is better to work with index notation. It just comes down to working out epsilon equal to delta and then rewrite it. It's basically, yeah, I mean, it's a little bit of a pain to do that, but you have to do it. It's good for your soul. So, okay, so kindly check this and get the structure constants. Okay, and there will be an assignment coming which will be covering which will let you play with a little bit more I mean gory details, especially SU3. I mean, you would see that it's 8-dimensional and there is something called the Gelman matrices, and you have to play with them. Okay.